In this video, we have to find the Crammer Rao Lower Bound for an unbiased estimator lambda, given the Poisson distribution with parameter lambda. How do we go about this? Solution. Of course, we recall that for the Cramer Rao inequality, which says 1 all over n into differential mean function of f of x. In this case, we have lambda as our parameter, the lambda squared is the Cramer Rao Lower Bound inequality. And now we are given the function for the Poisson distribution to be this. So it then means that in this function, we have to take the log, which is mean function of f of x lambda. We have to differentiate with respect to lambda. And we take the expectation, we will take the square as well, take the expectation and multiply with n. Also, we now say 1 all over whatever we have gotten here. Whatever we get, we compare it with what we are given. Now, given f of x lambda, which is equal to lambda x exponential negative lambda all over x factorial. This is what we are given. The first thing to do is for you to take the log. Which is the log mean function of f of x lambda. So we say take the log. If we take the log of this function, we have mean function of f of x lambda to be equal to, if we take the log of this, we have x mean lambda. If we take the log of an exponential raised to the power of negative lambda, we have negative lambda minus ln x factorial. This is what we get. So the next thing to do is to take the derivative with respect to lambda. So we take the derivative of this function with respect to lambda as it is here. So we say differentiate with respect to lambda. Differentiate. So we have differential of log of f of x lambda all over the lambda. So if we differentiate this function, what do we get? If we differentiate this, we get x all over lambda from calculus. If we differentiate this, we get 1. If we differentiate this, since there is no lambda here, we get 0. So this is also equal to x all over lambda minus 1. The next thing to do is to take this square. We now put this square here. We put this square. So we move over to this side of the board to do that. For more on this topic, you need to subscribe to this channel. So, for me to take the square, we will have differential mean function of x lambda into the lambda square to be equal to x all over lambda minus 1. We square this. Of course, from quadratic equation, we can expand this, which will give us x all over lambda squared minus 2x all over lambda plus 1 squared. which is still 1. So this is what we get if we expand this. It then means that we have x squared all over lambda squared minus 2x all over lambda plus 1. So this is what we get. The next thing is to take the expectation. So this becomes our function. So take the expectation. For me to take the expectation, we have to write it this way, as it is from the Crammer Rao Lower Bound inequality. The expectation of x squared all over lambda squared minus 2x all over lambda plus 1. So this is it. So what it means that we have to take the expectation of the function we have here. So for me to take the expectation, we move over to this other side of the board to put it down properly. So for more on this topic, you need to subscribe to this channel. So that means we can now write it this way: expectation of the differential mean function of f of x lambda all over the lambda squared to be equal to, if we take the expectation, we get expectation of x squared all over lambda squared minus 2 multiplied by the expectation of x all over lambda plus 1. So we say, but from Poisson distribution, our expected value of x is equal to lambda, and our expected value of x squared is equal to lambda squared plus lambda. So this is what we get. That's what we get. So we then know that anywhere we see expectation of x squared, we put lambda squared plus lambda. Anywhere we see expectation of x, we put lambda. So we have our expectation to be differential mean function of lambda all over lambda squared to be equal to, we have here lambda squared plus lambda all over lambda squared minus 2 lambda, our expected value of x is lambda all over lambda plus 1. So we can take the LCM of lambda squared. If you take the LCM of this and this, you have lambda squared all over this into this, will give us lambda squared plus lambda. This into this will give us minus 2 lambda squared, and this into this will give us plus lambda squared. Still the same thing. So we have we can write this to be, we move over to this side of the board, so it will be clearer. So this is what we get once we expand this. For more on this topic, you need to subscribe to this channel. So we have our expectation differential mean function of x lambda all over the lambda squared to be equal to, of course, we have lambda squared plus lambda minus lambda squared all over lambda squared. Of course, this can cancel this. We'll be left with lambda all over lambda squared, which is the same thing as 1 all over lambda. So we'll now compare it, we'll now input our n. So we'll say n, expectation of differential mean function of x lambda the lambda all squared is equal to n times 1 all over lambda, which is the same thing as n all over lambda for this. So by comparing with our Crammer Rao Lower Bound, we have, by comparing with our Crammer Rao Lower Bound, we have our Crammer Rao Lower Bound to be 1 all over n expectation of differential mean function of f of x lambda all over the lambda squared, which is equal to 1 all over n all over lambda. Would that mean that therefore our Crammer Rao which is differential mean function of f of x lambda the lambda all squared is equal to lambda all over n. So this becomes our answer for the Poisson distribution. So this becomes the Crammer Rao Lower Bound for the Poisson distribution given the parameter lambda. Computing the Crammer Rao Lower Bound inequality is quite simple when we follow the procedures we have in this video. For more on this topic, you need to subscribe to this channel.